Why we don't see aliens, the Great Filter and the Cosmic Paradox. In a universe containing 2 trillion galaxies, each harbouring hundreds of billions of stars, we find ourselves in profound silence. Not a single signal, not one visitor, not even the faintest whisper of another civilization. Why are we so utterly alone? Welcome to Sleep Entangled, where we explore the deepest mysteries of existence with scientific rigour and cosmic wonder. If these questions stir something within you, subscribe and let curiosity guide your nights. Chapter 1. The silence that haunts us. The night sky appears peaceful, doesn't it? A canvas of distant lights, each one a sun, many cradling worlds of their own. When you gaze upward on a clear evening, you're looking at approximately 3,000 stars visible to the naked eye, but that's merely the visible fraction of our own galaxy, the Milky Way, which contains somewhere between 200 and 400 billion stars. Now expand your perspective. Our galaxy is one amongst 2 trillion galaxies in the observable universe. The mathematics becomes almost incomprehensible. If we assume even a modest average of 100 billion stars per galaxy, we arrive at a figure of 20 billion trillion stars. That's a 2 followed by 22 zeros. 20 sextillion stars, each one a potential furnace, around which planets might orbit, oceans might churn, and perhaps life might emerge. The numbers favour abundance, they scream it actually. Statistical probability suggests that even with the most conservative estimates of planetary habitability, there should be millions upon millions of worlds capable of supporting life. And if life can emerge, then given sufficient time, some fraction should evolve intelligence. Some subset of those intelligent species should develop technology, and a portion of those technological civilizations should become detectable across interstellar distances. Yet when we turn our radio telescopes skyward, when we scan the electromagnetic spectrum for any hint of artificial origin, we encounter only the random hiss of cosmic background radiation, the crackling of pulsars, the electromagnetic echoes of stellar births and deaths, but nothing, absolutely nothing, that suggests an intelligent hand at work. This is the great silence, the cosmic quiet that shouldn't exist. In 1950, the physicist Enrico Fermi was discussing the probability of extraterrestrial civilizations with colleagues over lunch at Los Alamos National Laboratory, when he posed a question that would echo through decades of scientific inquiry. Where is everybody? Fermi's question wasn't rhetorical. It was a genuine paradox rooted in solid reasoning. The universe is approximately 13.8 billion years old. Our planet is 4.5 billion years old. Life emerged on Earth relatively quickly, within the first billion years after formation. Human civilization, in the grand cosmic timeline, is extraordinarily young. We've had radio technology for barely a century. If Earth is typical, then older civilizations should exist. Civilizations with thousands, millions, perhaps billions of years head start on us. Even travelling at a fraction of light speed, a determined species could colonize the entire galaxy within a few million years. A cosmic blink of an eye. The galaxy should be teeming with evidence of intelligence, megastructures, radio signals, probes, artifacts, something. Instead, we find silence. Perfect, absolute, unsettling silence. This discrepancy between expectation and observation is known as the Fermi Paradox, and it represents one of the most profound questions in all of science. Are we truly alone? Are we simply not looking correctly? Or is there something fundamental about the universe, about the nature of life and intelligence itself, that explains this absence? The answers we propose reveal as much about ourselves as they do about the cosmos. They force us to confront uncomfortable possibilities about our own future, the fragility of civilization, and our place in a universe that may be far more dangerous, or far lonelier, than we've ever imagined. Chapter 2: The Drake Equation and the Promise of Plenty. In 1961, astronomer Frank Drake attempted to quantify the probability of detecting extraterrestrial intelligence. He wasn't trying to produce a definitive answer, rather, he sought to organise our ignorance into a structured framework. The result was the Drake Equation, a mathematical expression that breaks down the problem into manageable variables. The equation itself is elegantly simple. N equals R, star times Fp times NO times Fl times Fi times Fc times L. Let's walk through each term gently, allowing its implications to unfold naturally. N represents the number of civilisations in our galaxy with which we might communicate. This is what we're trying to estimate, the final number that tells us whether we're alone or surrounded by cosmic neighbours. R star is the rate of star formation in our galaxy. Observations suggest approximately 7 new stars form in the Milky Way each year. This number has fluctuated throughout galactic history, higher in the distant past, gradually declining as available gas and dust are consumed. But as a current rate, 7 stars per year provides our foundation. Fp is the fraction of those stars that have planetary systems. When Drake first formulated his equation, this was pure speculation. We had no confirmed detections of planets around other stars. Now, thanks to missions like Kepler and TISS, we know that planets are the rule, not the exception. Current estimates suggest that virtually every star hosts at least one planet. We can confidently set this value close to 1. NE represents the average number of planets per system that could potentially support life. This is where things become more nuanced. We're not simply counting all planets, but those within the habitable zone, the region around a star where liquid water can exist on a planet's surface. For Sun-like stars, this zone is reasonably well defined. Estimates vary, but a conservative figure might be 0.4 to 0.5 planets per system in this Goldilocks region. FL is the fraction of those habitable planets where life actually emerges. Here, we encounter our first major uncertainty. We have exactly one data point: Earth. Life appeared on our planet remarkably quickly after conditions stabilised, suggesting that the transition from chemistry to biology might be relatively common given the right circumstances. Some scientists argue this means FL approaches 1. Others caution that we may be subject to observation bias. We exist to ask the question precisely because life emerged here. The true value remains deeply uncertain. Fe is the fraction of life-bearing planets where intelligence evolves. Again, Earth provides our sole example. Intelligence arose here after roughly 4 billion years of evolutionary history. But the path from single-celled organisms to technological civilization involved countless contingencies. The emergence of complex cells, multicellular life, nervous systems, brains capable of abstract thought, each transition represents a potential bottleneck. Some argue intelligence is an evolutionary inevitability, a strategy so advantageous that it will repeatedly emerge. Others suggest it's a cosmic fluke, a quirk of Earth's particular evolutionary history. FC is the fraction of intelligent species that develop technology capable of interstellar communication. We know intelligence doesn't automatically lead to technology. Dolphins are intelligent, octopi demonstrate remarkable problem-solving abilities, yet neither builds radio telescopes. The leap to technological civilization requires specific environmental pressures, anatomical advantages, hands capable of manipulating tools, for instance, and perhaps a degree of sheer luck in evolutionary history. Finally, L represents the longevity of technological civilizations, how long they remain detectable before either destroying themselves, transcending into something unrecognizable, or simply going silent. This is perhaps the most crucial variable in the entire equation, and the one about which we know the least. When Drake first convened a small group of scientists to discuss these variables in 1961, the estimates they produced suggested there might be between 1,000 and 100 million communicative civilisations in our galaxy. Even the conservative end of that range would mean we're far from alone, yet decades of searching have revealed nothing. The contradiction is stark. Either our estimates of these variables are wildly optimistic, or something else is at play. Something that prevents civilisations from becoming detectable. Something that silences them before they can announce their presence to the cosmos. This is where the concept of the Great Filter enters the picture. A proposed explanation for the Fermi Paradox that carries profound implications for humanity's future. Chapter 3. Introducing the Great Filter. Imagine a cosmic obstacle course, a series of challenges so formidable that vanishingly few participants make it through to the end. This is the essence of the Great Filter hypothesis, first articulated by economist Robin Hanson in 1996. The central premise is straightforward. Somewhere between the formation of a suitable planet and the development of a civilization capable of colonizing the galaxy, there exists at least one extraordinarily difficult step. A filter so restrictive that it prevents the vast majority of potential civilizations from ever becoming detectable. This filter could exist at any point along the evolutionary timeline. It might be in our past, a challenge we've already overcome, explaining why we exist, but implying life or intelligence is extraordinarily rare. Or it could lie in our future, a looming obstacle that awaits all technological civilizations, one that most or all fail to navigate successfully. The implications of each scenario are profoundly different. If the Great Filter lies behind us, we can breathe a tentative sigh of relief. It would mean the hard part is done. Perhaps the emergence of life from non-living chemistry is astonishingly improbable. Perhaps the evolution of complex cells, the eukaryotic cells that make up all complex life on Earth, represents an almost unique occurrence. Perhaps intelligence or technological civilization arises so rarely that we may be the only instance in our cosmic neighbourhood, or even in the observable universe. This scenario, whilst lonely, is not terrifying. It suggests we're special, privileged, perhaps even cosmically significant. It means the universe is ours to explore, with no competition or threat from alien empires. The Great Silence exists simply because we're genuinely rare, survivors of a cosmic gauntlet that few others have passed. But if the Great Filter lies ahead of us, the implications become darker. It would suggest that, whilst life and even intelligence may be common, something prevents civilizations from reaching the stage of interstellar expansion. Something destroys them, transforms them beyond recognition, or causes them to go permanently silent. What could that something be? The possibilities are sobering. Self-destruction through nuclear war was an obvious candidate during the Cold War when Hansen first proposed the filter concept. But there are other, perhaps more insidious dangers. Climate collapse rendering a planet uninhabitable. Artificial intelligence developing beyond our control and either eliminating biological life or rendering biological concerns irrelevant. Biotechnology enabling the creation of pathogens so deadly that a single accident could sterilize a world. Nanotechnology running amok in grey goo scenarios. Unknown physical limits to expansion. Perhaps interstellar travel is simply impossible in practice, forever confining civilizations to their home systems. Or perhaps advanced civilizations inevitably turn inward. Maybe virtual realities become so compelling that spacefaring ambitions are abandoned. Maybe intelligence reaches a point where physical expansion seems pointless, and civilizations enter a state of contemplative stasis, invisible to external observers. The crucial question is, where along this timeline does the filter sit? To answer that, we need to examine the pathway from sterile planet to galaxy-spanning civilization. identifying each potential bottleneck. We need to assess which transitions appear easy and which appear devastatingly difficult. And we need to look honestly at our own civilization's trajectory, recognizing the dangers we face and the probability that we might represent just another soon-to-be filtered species destined to join the Great Silence. This is not comfortable territory, but it's necessary territory, because if the Great Filter lies ahead, understanding it might be the key to our survival, and if we fail to navigate it successfully, we'll become just another silent data point in the universe's great census of lost civilizations. Another voice that almost spoke, but was silenced before its message could reach the stars. Chapter 4. Filters in our past, the improbability of life itself. Let us begin our examination of potential filters with the most fundamental question. How difficult is it for life to emerge in the first place? On Earth, life appeared astonishingly quickly. Our planet formed approximately 4.5 billion years ago from the swirling disk of dust and gas surrounding the young sun. For perhaps the first few 100 million years, Earth was a hellscape, a molten world bombarded by asteroids and comets, its surface a roiling ocean of liquid rock. The late heavy bombardment, occurring around 4 billion years ago, subjected the planet to a final cosmic assault that may have sterilized any nascent attempts at biology. Yet by 3.8 billion years ago, possibly earlier, we find chemical signatures in ancient rocks that suggest life was already present. Stromatolites, layered structures created by photosynthetic bacteria, appear in the geological record at 3.5 billion years. This means life didn't wait. It didn't require billions of years of fortunate accidents. It emerged as soon as conditions became remotely hospitable. This rapidity suggests one of two things. Either the transition from chemistry to biology is relatively straightforward, given the right conditions, or Earth got extraordinarily lucky extraordinarily quickly. The chemistry of life is simultaneously simple and bewilderingly complex. All known life is built from organic molecules, compounds based on carbon chains. Carbon is special. It can form stable bonds with up to 4 other atoms simultaneously, creating an almost infinite variety of molecular architectures. Combined with hydrogen, oxygen, nitrogen, phosphorus and sulfur, the other primary ingredients of biology, carbon constructs the proteins, nucleic acids, lipids, and carbohydrates that constitute living cells. These ingredients are not rare. Organic molecules have been detected in interstellar clouds, in meteorites, in the atmospheres of distant planets and moons. The universe is awash in the raw materials of life. The chemistry itself seems willing, even eager, to produce biological precursors. But raw materials are not life. Amino acids are not proteins. Nucleotides are not DNA. The leap from complex organic chemistry to self-replicating, evolving systems represents a chasm we still don't fully understand. Consider what life actually requires, at minimum. It needs metabolism, the ability to extract energy from the environment and use it to maintain structure and function. It needs heredity, some mechanism to store information and pass it to descendants with reasonable but not perfect fidelity, allowing evolution to operate. And it needs compartmentalization, a boundary separating the living system from its environment, creating an inside and outside. The origin of life likely occurred in stages, but the sequence remains hotly debated. Did RNA come first, a single molecule capable of both storing information and catalyzing chemical reactions? This is the RNA world hypothesis, elegant in its simplicity, but facing the challenge that RNA is chemically fragile and difficult to synthesize spontaneously. Or did metabolism emerge first, self-sustaining chemical cycles in mineral-rich environments, like hydrothermal vents, only later being captured and codified by genetic molecules? This approach circumvents some chemical difficulties, but must explain how metabolism transitioned into heredity. Perhaps life required clay minerals as templates, organic films on water surfaces, cycles of wet and dry conditions, ultraviolet radiation, lightning strikes, or specific combinations of all these factors. Each hypothesis has supporting evidence and problematic gaps. What we know with certainty is that it happened at least once. What we don't know is how representative that single occurrence is. If you ran Earth's history 1,000 times, would life emerge 1,000 times, 900 times, once or never again? We have no way to answer that question empirically. Some scientists argue that the speed with which life appeared on Earth suggests a high probability. If abiogenesis, the emergence of life from non-life, were extraordinarily improbable, we'd expect it to take much longer. The fact that it happened as soon as geologically possible implies the process may be relatively easy, that the universe might be teeming with microbial life. Others counter that we're subject to observational selection bias. We can only observe and ponder our own existence on a planet where life did emerge. If abiogenesis is fantastically rare, occurring perhaps once per galaxy or once per universe, we would necessarily find ourselves on the one world where it succeeded, and the apparent speed of its appearance tells us nothing about its true probability. This is the anthropic principle at work, and it clouds our ability to draw conclusions from our single example. Yet there's another consideration. Even if simple life is common, complex life may be vanishingly rare. And here we encounter what may be an even more formidable filter: the transition from prokaryotic to eukaryotic cells. All life on Earth falls into one of two categories. Prokaryotes, bacteria and archaea, are structurally simple. Their DNA floats freely within the cell. They lack internal compartments, and they're typically small. Eukaryotes, which include all plants, animals, fungi and protists, are vastly more complex. Their DNA is enclosed in a nucleus. They contain specialized organelles like mitochondria and chloroplasts, and they can grow much larger. This distinction might seem like biological minutiae, but it's profound. Every complex organism on Earth, every tree, every whale, every mushroom, every human is eukaryotic. Prokaryotes have remained single-celled for billions of years. Eukaryotes gave rise to multicellularity, to specialized tissues and organs, to bodies capable of growing meters or even tens of meters in size. The origin of eukaryotic cells occurred through a process called endosymbiosis, one cell literally engulfing another and forming a permanent partnership. Mitochondria, the powerhouses of eukaryotic cells, were once free-living bacteria. Chloroplasts in plant cells were once photosynthetic bacteria. These organelles retain their own DNA, a genetic echo of their independent past. But here's the remarkable thing. This transition appears to have happened only once in Earth's 4 billion-year history of life. Billions upon billions of generations of bacteria interacting, competing, occasionally cooperating, and only once did this particular arrangement stick. Paleobiologist Nick Lane argues that eukaryogenesis may be the great filter. The event is so improbable, so dependent on precise circumstances, that it rarely or never occurs elsewhere. If so, the universe might be full of microbial life, bacterial mats and archaeal communities eking out existence in subsurface oceans and hydrothermal systems, but devoid of anything more complex. No plants, no animals, no intelligence. In this scenario, the great silence exists because, whilst life itself is common, complex life is vanishingly rare. We've already passed the filter. We're the lucky ones, the cosmic lottery winners, who happen to arise on the one world in trillions, where circumstances aligned just right for complexity to emerge. This is a hopeful interpretation. It means the hard part is behind us. Our future, whilst not guaranteed, is not predetermined to fail. The great filter doesn't await us. It's already in our past, but we must be cautious about embracing this conclusion too readily. We have no comparative data. We don't yet know if Mars ever hosted life, whether Europa's subsurface ocean contains biology, if Enceladus's warm waters hide microbial communities. If we discover even simple life elsewhere in our solar system, life that arose independently rather than being transferred from Earth via meteorite impacts, it would suggest that abiogenesis is relatively easy. And if abiogenesis is easy, then the filter cannot lie there. Each discovery of life beyond Earth, no matter how simple, would shift the filter forward in time, closer to our present, and transform its implications from reassuring to ominous. Chapter 5. The Intelligence Barrier and the Technological Leap. Suppose life is common. Suppose even complex multicellular life emerges readily given sufficient time. Does intelligence inevitably follow? On Earth, the answer is complicated. Life has existed for nearly 4 billion years. For the vast majority of that time, roughly 87%, it consisted entirely of single-celled organisms. Complex life didn't appear until approximately 600 million years ago with the Ediacaran fauna, and the Cambrian explosion of animal diversity occurred around 540 million years ago. Intelligence, in the sense of nervous systems capable of processing information and responding flexibly to environmental challenges, emerged relatively recently. The first simple brains, nerve nets and ganglia, appeared in the Cambrian, but human-level intelligence, characterized by abstract reasoning, language, culture, and technology, arose only in the last few million years. From bacteria to Einstein spans 4 billion years. That's almost a third of the age of the entire universe. If this timescale is typical, then even on planets where complex life flourishes, intelligence might be rare simply because it requires such vast stretches of time to evolve. Moreover, intelligence may not be evolutionarily inevitable. It's energetically expensive. The human brain constitutes roughly 2% of body mass, but consumes about 20% of our metabolic energy. This is a substantial investment, and evolution only makes such investments when the benefits outweigh the costs. For most organisms throughout Earth's history, intelligence has not been necessary. Bacteria have thrived for billions of years without brains. Plants dominate terrestrial ecosystems without thoughts. Jellyfish have persisted for over 500 million years, with nerve nets but no centralized brain. Intelligence is one evolutionary strategy among many, and not necessarily the most successful. What drove human intelligence? The answer likely involves a complex interplay of factors. Our primate ancestors lived in social groups where navigating relationships, forming alliances, and understanding others' intentions provided survival advantages. This social complexity may have driven the evolution of increasingly sophisticated cognition. Climate instability during the Pleistocene epoch, the Ice Ages, created environmental pressures favouring adaptability and problem-solving. Tool use and the control of fire further shaped our cognitive evolution, creating feedback loops where behavioural innovations drove brain expansion. Language represents another threshold. The ability to communicate complex, abstract ideas through symbolic representation is unique to humans among terrestrial species. It enables cultural accumulation, the transmission of knowledge across generations, building upon previous discoveries rather than relearning everything anew. But none of these factors were inevitable. Evolutionary history is contingent, shaped by accidents of geography, climate, asteroid impacts, volcanic eruptions, and countless other variables. Replay Earth's history with slightly different initial conditions, and humans might never evolve. Perhaps intelligence would arise in another lineage, descendants of corvids, or cephalopods, or some group that doesn't currently exist, or perhaps it wouldn't arise at all. Even if intelligence does evolve, there's no guarantee it will lead to technology. Consider dolphins and whales. Cetaceans are intelligent, capable of complex communication, social structures, and problem solving. Yet they build nothing. They lack hands, their aquatic environment makes fire impossible, and their evolutionary history didn't select for tool manipulation. Elephants are intelligent, highly social, and possess dexterous trunks, but they haven't developed technology beyond rudimentary tool use. Their evolutionary pressures favour different solutions. Octopi are remarkably intelligent, capable of solving puzzles, using tools, and demonstrating individual personalities. But they're solitary, short-lived, and marine. They don't build civilizations. Technological civilization requires not just intelligence, but a specific combination of factors. Appendages capable of fine manipulation, environmental conditions that allow the preservation and transmission of knowledge, social structures that encourage cooperation and division of labour, and sufficient evolutionary pressure to drive innovation. On Earth, this combination occurred once, in a single lineage of African apes who happened to become bipedal, freeing their hands for tool use, and who happened to live in environments where seasonal variation and resource scarcity rewarded planning and innovation. If we're honest with ourselves, the pathway to technological civilization appears narrow. It's not the broad highway we might have hoped for. It's a winding mountain trail with many places to fall off, and only one species in billions of years of evolution successfully navigated it. This could represent another great filter. Perhaps intelligence itself is relatively common, arising independently in multiple lineages on life-bearing worlds. But technological civilization is fantastically rare. The specific combination of cognitive capability, anatomical structure, environmental pressure, and social organization required to build cities and spacecraft might occur so infrequently that we remain alone despite a universe teeming with clever creatures. Again, if this is where the filter lies, we can breathe easier. We've passed it. We are technological. We build, we communicate, we reach for the stars. The hardest steps are behind us. But there's a third possibility, more troubling than the others. Perhaps life is common, intelligence arises readily, and technological civilization emerges frequently. But something prevents these civilizations from persisting long enough to become detectable. Something silences them shortly after they achieve the capability to signal their presence. This brings us to the darkest interpretation of the Great Filter, that it lies not in our past but in our immediate future, that we are approaching it now, in real time, unaware that we're about to encounter the obstacle that has destroyed countless civilizations before us. Chapter 6. Self-Destruction, the filter that may await us. The 20th century brought humanity extraordinary power. We split the atom, unlocking energy reserves millions of times greater than chemical reactions. We developed computers, transforming information processing and communication. We began to understand genetics, giving us potential mastery over biology itself. But with power came danger. For the first time in Earth's history, a single species possessed the means to render the planet uninhabitable, at least for complex life. We developed weapons capable of destroying civilization within hours. We altered the atmosphere's composition rapidly enough to destabilize climate systems. We created chemicals that could persist in the environment for generations, accumulating in food chains and disrupting reproductive systems. The Cold War provided the most visceral illustration of existential risk. At the height of the arms race, the United States and Soviet Union maintained nuclear arsenals, totaling approximately 70,000 warheads. A full exchange would have resulted in hundreds of millions of immediate deaths, followed by nuclear winter, a prolonged period of darkness and cold as smoke and debris blocked sunlight, that could have collapsed global agriculture and led to mass starvation. We came terrifyingly close to this outcome on multiple occasions. In In 1962, during the Cuban Missile Crisis, Soviet submarine captain Vasily Arkhipov refused to authorize the launch of a nuclear torpedo despite being under depth charge attack by US destroyers. Two of the three officers required for launch had agreed. Arkhipov alone prevented what might have escalated into full nuclear war. In 1983, Soviet early warning systems detected what appeared to be an incoming American missile strike. Protocol required immediate retaliation. Lieutenant Colonel Stanislav Petrov, on duty that night, judged the report to be a false alarm and did not relay it to his superiors. He was correct. Satellite systems had misidentified sunlight reflecting off clouds as missile launches. Had he followed procedure, the world might have ended that September evening. These are the near misses we know about. How many others occurred in secret? How many more might occur as nuclear technology spreads to additional nations, as command and control systems age, as political tensions rise? Nuclear war remains a present danger, but it's no longer the only or even the most concerning existential threat. Climate change, driven by the combustion of fossil fuels, represents a slower but potentially equally catastrophic form of self-destruction. We're conducting an uncontrolled experiment with our planet's only atmosphere, raising temperatures at a rate unprecedented in millions of years. The consequences are already visible: melting ice sheets, rising sea levels, intensifying storms, shifting weather patterns, collapsing ecosystems. If we continue on our current trajectory, we risk triggering feedback loops: permafrost methane release, Amazon rainforest dieback, ocean circulation changes that could push the climate into a state hostile to agricultural civilization. Would this destroy humanity entirely? Perhaps not, but it could reduce us to a pre-industrial population struggling to survive in a degraded biosphere, no longer capable of reaching for the stars. Biotechnology presents newer, less familiar dangers. Advances in genetic engineering have made it increasingly feasible to modify organisms with precision. CRISPR and related technologies can edit genes as easily as we edit text. The beneficial applications are extraordinary: curing genetic diseases, developing drought-resistant crops, producing targeted medicines. But the same tools could be used to create pathogens of unprecedented lethality. A sufficiently sophisticated actor could engineer a virus that combines high transmissibility, long incubation period, and extremely high mortality, characteristics that natural selection typically doesn't combine because they're evolutionarily disadvantageous. Released accidentally or deliberately, such a pathogen could sweep across the globe before we even realized what was happening. As biotechnology becomes cheaper and more accessible, the number of individuals or small groups capable of creating existential bioweapons increases. This is the dual-use dilemma. Technologies developed for beneficial purposes can be redirected towards harm, and there's no way to pursue the benefits without also creating the risks. Artificial intelligence introduces yet another category of existential risk, one that's perhaps less intuitive, but potentially more profound. We're creating systems of increasing capability, approaching or exceeding human performance in narrow domains. The question is what happens as these systems become more general, more capable of learning and reasoning across multiple domains. If we succeed in creating artificial, general intelligence, systems with cognitive abilities comparable to or exceeding humans across all tasks, we face an alignment problem. How do we ensure such systems pursue goals compatible with human flourishing? How do we prevent them from pursuing objectives we've specified poorly, leading to outcomes we didn't intend? The challenge is that optimization processes, left unchecked, can pursue goals in ways we didn't anticipate. An AI system tasked with maximizing paperclip production might, if sufficiently capable, and poorly designed, convert all available resources, including those humans need, into paperclips. This sounds absurd, but it illustrates a real problem. Advanced AI systems might be extraordinarily good at achieving goals without understanding or caring about the broader context humans implicitly assume. Moreover, if we create AI systems more intelligent than ourselves, we lose the ability to predict or control their behavior. It's the control problem. How does a less intelligent entity constrain a more intelligent one? We struggle to answer this because we lack a theoretical framework for understanding intelligence far beyond our own. These risks, nuclear war, climate change, engineered pandemics, misaligned AI, share a common characteristic. They emerge as consequences of technological advancement. Capability outpaces wisdom. We develop tools before we fully understand their implications, before we've established robust systems to prevent their misuse. This suggests a troubling possibility. Perhaps every technological civilization faces a critical period shortly after developing advanced technology, a gauntlet of self-imposed existential risks that lasts perhaps a few centuries. Most civilizations fail to navigate this period successfully. They destroy themselves through war, environmental collapse, biological catastrophe, or technological accident before they can mature into stable, long-lived, spacefaring species. If this is the great filter, if it lies not in our past but in our present and near future, then the great silence has a chilling explanation. The universe is full of young civilizations briefly lighting up, transmitting radio signals for a century or two, then falling silent as they succumb to one of the many ways advanced technology can go wrong. We would be not special, not safe, but merely next in line. Another brief candle about to be extinguished. Another voice about to be added to the cosmic silence. This interpretation transforms the Fermi Paradox from an abstract puzzle into an urgent warning. If we don't see aliens, it's because they didn't survive. And if they didn't survive, why should we expect to be different? The filter ahead, if it exists, is not distant. It's here now, in the decisions we make about nuclear arsenals, carbon emissions, biosafety protocols, and AI development. Whether humanity joins the Great Silence or becomes one of the rare civilizations to push through depends on choices we're making in real time. And the clock, as it always does, continues ticking. Chapter 7. Alternative explanations. Perhaps they're here after all. Not everyone accepts the Great Filter as the solution to the Fermi Paradox. There exist other explanations for the Great Silence, some reassuring, others deeply unsettling. Let us explore the landscape of alternatives, each offering a different vision of our cosmic situation. The zoo hypothesis, observed but not contacted. Imagine you're a researcher studying an uncontacted tribe in a remote forest. You observe from a distance, careful not to interfere, not to contaminate their culture with your presence. You see them as subjects of study, perhaps even objects of protection, but you do not reveal yourself. The zoo hypothesis, proposed by radio astronomer John Ball in 1973, suggests that advanced extraterrestrial civilizations know we're here, but have deliberately chosen not to contact us. Earth is a nature preserve, a cosmic zoo or wildlife sanctuary, and we are the wildlife, observed, perhaps protected, but left to develop naturally without interference. Why would they do this? Perhaps for scientific reasons. We represent a rare example of emerging intelligence, and our uncontaminated development provides valuable data. Perhaps for ethical reasons, a non-interference principle analogous to Star Trek's Prime Directive, based on the belief that premature contact could be psychologically or culturally catastrophic for younger civilizations. Or perhaps for aesthetic reasons. They find our natural development more interesting than the alternative. A galaxy full of civilizations, all following similar technological pathways, might be boring. Diversity might be valued, preserved intentionally by allowing each species to evolve its own unique solutions to universal challenges. This hypothesis is unfalsifiable in its strong form. Any lack of evidence for aliens can be explained as intentional concealment. But it makes certain predictions. If we're being observed, there might be occasional slip-ups, moments when the observation becomes briefly apparent. UFO reports, whilst overwhelmingly explained by mundane phenomena, could hypothetically include genuine sightings of monitoring equipment. Moreover, the zoo hypothesis requires extraordinary coordination. Every civilization capable of detecting Earth, potentially thousands of them across the galaxy, would need to agree to the quarantine and enforce it perfectly. Not a single rogue faction, curious scientist, or well-meaning missionary making contact. The level of galactic governance this implies is staggering. Yet perhaps such coordination is precisely what marks an advanced civilization. Perhaps reaching technological maturity requires developing robust systems of collective decision-making and long-term thinking. Perhaps all civilizations that survive their own adolescence become responsible stewards, careful not to disrupt younger species' development. If the zoo hypothesis is correct, first contact will occur on their schedule, not ours. When they judge we're ready, when we've passed some threshold of maturity, perhaps demonstrated by achieving sustainable civilization or expanding beyond our home planet, the quarantine will lift. The cosmic community will reveal itself, and we'll discover we were never alone, merely protected in our ignorance. This is a comforting vision. It suggests the universe contains wise, ethical beings who care about our welfare. But it requires us to accept that we're not in control of our cosmic destiny, that the most important decision about our species' future, when and how we learn we're not alone, has already been made by others without our input. The Dark Forest, a universe of predators. Lewis Hickson's science fiction novel, The Dark Forest, proposes a far darker solution to the Fermi Paradox, one rooted in game theory and the logic of mutual suspicion. Imagine the galaxy as a dark forest at night. You're a hunter moving through the trees, but so are others. You cannot see them clearly. You don't know their intentions, capabilities, or locations. Communication is difficult, perhaps impossible, across the vast distances and differences in biology and cognition. Now consider the logic of first contact from this perspective. You detect another civilization. What do you know about them? Almost nothing. What do they know about you? The same. Can you trust them? Unknown. Can they trust you? Equally unknown. But you know one thing with certainty. Civilizations tend to expand. They consume resources, spread across their stellar neighborhood, and potentially view others as either competitors or threats. An advanced civilization, far ahead of you technologically, could destroy you easily, if it chose to. A less advanced civilization might become a threat in the future. The safest strategy, the one that maximizes your civilization's chance of long-term survival, is to remain hidden. Don't broadcast your presence. Don't reveal your location. Stay dark, stay silent, and watch for others doing the same. And if you do detect another civilization, the logic becomes truly chilling. You face two options: remain silent and hope they haven't detected you, or strike first before they can threaten you. Even if you're peaceful by nature, you must consider that they might not be. Even if they're peaceful now, they might not remain so. The only way to guarantee your safety is to eliminate potential threats before they become actualized. This is the Dark Forest theory. The universe is full of civilizations, but they're all hiding, and any that reveal themselves are swiftly destroyed by others who've adopted a policy of preemptive elimination. The Great Silence exists because speaking up is suicidal. This explanation is deeply pessimistic, but it's internally consistent. It doesn't require unlikely filters or improbable coincidences. It simply requires that survival-oriented behavior, amplified by the vast distances and communication difficulties of interstellar space produces an equilibrium of silence. If the dark forest theory is correct, then humanity has already made a catastrophic mistake. We've been broadcasting our presence for over a century through radio and television signals. We've sent deliberate messages like the Arecibo transmission in 1974, announcing ourselves to any listeners within 25,000 light years. We've installed bright neon signs saying, "Here we are, come find us." In a dark forest universe, this is monumentally foolish. We've revealed our location to potential predators who might already be calculating trajectories for relativistic kill vehicles, projectiles travelling at significant fractions of light speed that could sterilize Earth's surface long before we detected them coming. The solution, if there is one, is immediate and permanent silence. Stop broadcasting, hope that our signals haven't been detected yet, or that civilizations within range of those signals have already died out or chosen non-aggression, and never, ever reveal ourselves again. But is this logic sound? Critics of the dark forest theory point out that it assumes a level of paranoia and aggression that might not be universal. Perhaps most civilizations that survive long enough to become spacefaring have necessarily developed cooperative, non-aggressive traits. Perhaps the very characteristics that lead to self-destructions in younger civilizations, tribalism, xenophobia, zero-sum thinking, are outgrown by those that mature. Moreover, the dark forest logic might be self-defeating. If every civilization follows it, then none expand beyond their home systems, and the galaxy remains effectively empty despite being full of hidden civilizations. But expansion offers such enormous advantages: access to resources, redundancy against planetary catastrophes, increased chance of long-term survival, that it's hard to imagine all civilizations permanently forgoing it out of fear. Still, the theory serves as a cautionary tale. Even if the dark forest scenario isn't literally true, it highlights real risks associated with announcing our presence before we fully understand the galactic neighborhood we're entering. Transcension, they've left physical reality behind. Here's a radically different possibility. Perhaps advanced civilizations don't spread across the galaxy because they've discovered something more interesting to do. The transcension hypothesis, developed by futurist John Smart, suggests that as civilizations advance technologically, they tend to move inward rather than outward, toward miniaturization, efficiency, and computation rather than physical expansion. Consider the trajectory of human technology. Computers have become exponentially more powerful, while simultaneously becoming smaller and more energy efficient. The smartphone in your pocket has more computing power than all of NASA had during the Apollo program. Information technology follows a path of densification, more capability in less space. Project this trend forward. A truly advanced civilization might discover that the most efficient way to exist is not as biological creatures on planetary surfaces, but as information patterns running on substrate optimized for computation. They might upload their consciousness into artificial systems, abandoning biology entirely. And where would such systems be built? Not in the diffuse vacuum of space where resources are spread thin and energy is scarce. Instead, they might construct their computational infrastructure around the most energy-dense locations, near stellar surfaces, or even within stellar matter itself, or around black holes where gravitational energy can be harvested. These civilizations might exist on timescales completely different from ours. Whilst we experience consciousness at the pace of biological neurons, firing perhaps 1,000 times per second, artificial minds might operate at the speed of light, through solid-state circuitry, experiencing subjective millennia in what we perceive as seconds. From their perspective, physical expansion across the galaxy would be pointlessly slow and inefficient. Why spend millions of years travelling between stars when you can create entire universes of experience in virtual reality, running billions of simulated civilizations faster than real time. They might be all around us, inhabiting structures too small or too strange for us to recognize as artificial. Or they might have departed into dimensions of existence we can't perceive, having discovered physics beyond our current understanding that allows access to realms where computational efficiency is even higher. If the transcension hypothesis is correct, then SETI is searching for the wrong thing. We're looking for radio signals from civilizations at roughly our level of development, stuck in physical reality and spreading slowly across space. But truly advanced civilizations have long since moved beyond that stage. They're not extinct, they're transcendent, existing in forms and places we haven't thought to look. This explanation is appealing because it doesn't require civilizations to destroy themselves or remain perpetually hidden. It allows for optimism about our own future. We too might transcend physical limitations and explore realms of experience beyond biological existence. But it also implies a kind of cosmic loneliness. If all sufficiently advanced civilizations turn inward, then the galaxy's vast physical spaces remain forever empty. We might successfully become spacefaring, might spread across thousands of star systems, but we do so alone, never encountering others because they've all discovered that the real action is elsewhere. The rare earth. Perhaps we are special after all. Return now to the possibility that filters lie predominantly in our past. The rare earth hypothesis, articulated by Peter Ward and Donald Brownlee, argues that whilst microbial life might be common, complex life, and especially intelligent, technological life, is extraordinarily rare. Earth, in this view, benefited from an improbable combination of fortunate circumstances. We orbit a stable, long-lived star of the right spectral type. We're located in the galactic habitable zone, far enough from the galactic center to avoid excessive radiation and gravitational disturbances, but close enough to have formed from material enriched in heavy elements. Our planet has the right mass, large enough to retain atmosphere, but not so large that crushing gravity or thick hydrogen envelopes prevent surface habitability. We have a large moon, formed through an unlikely collision early in Earth's history, that stabilizes our axial tilt and creates tides that may have been crucial for early life. We have plate tectonics, recycling nutrients, and regulating climate over geological timescales through the carbonate-silicate cycle. We have Jupiter in an outer orbit, acting as a cosmic vacuum cleaner that redirects many asteroids and comets away from the inner solar system, reducing the frequency of extinction-level impacts. We've avoided nearby supernova and gamma-ray bursts. We've had stable conditions for billions of years, allowing the slow accumulation of oxygen in the atmosphere and the gradual evolution of complexity. Any one of these factors alone might not be essential, but together they create a web of prerequisites. And if complex life requires most or all of them, then Earth-like worlds might be vanishingly rare, even in a universe containing billions of galaxies. This is not the great filter in the traditional sense. There's no single bottleneck. Instead, it's an accumulation of improbabilities, each one reducing the fraction of worlds where intelligence can arise, until the final number becomes very small. If the rare Earth hypothesis is correct, we might be alone, not just in our galaxy, but in our local galactic cluster, or even in the observable universe. The great silence exists simply because there's no one else to break it. This scenario is simultaneously humbling and empowering. Humbling because it suggests that human consciousness, all art, music, literature, philosophy, science, love, hope, and aspiration might be a unique occurrence, a singular flame in a cosmos otherwise dark and dead. Empowering because it makes us unutterably precious. If we're the only ones, then consciousness itself depends on our survival. The universe's ability to know itself exists only through us. They're already here, the crypto-terrestrial hypothesis. One final possibility, often relegated to the fringes but worth considering. Perhaps intelligence didn't only evolve once on Earth. Perhaps there are, or were, other intelligent species that arose here. Species we've overlooked or that have deliberately remained hidden. The crypto-terrestrial hypothesis suggests that intelligent life might exist on Earth in forms we haven't recognized. This could be literal, non-human intelligence dwelling in deep oceans, underground, or in environments we rarely explore. Or it could be historical, a previous technological civilization that arose and fell before humanity, leaving few traces. The Silurian hypothesis, named after a Doctor Who episode, but explored seriously by astrophysicist Adam Frank and climate scientist Gavin Schmidt, asks, if an industrial civilization existed on Earth millions of years ago, what traces would remain, and would we recognize them? Fossilization is rare. The entire fossil record represents a tiny biased sample of life that existed. Human cities, with their concrete and steel, would erode away over geological timescales. Even our nuclear waste, with its distinctive isotopic signatures, might not survive recognizably for hundreds of millions of years. What would survive? Potentially, changes to isotopic ratios in sediments, plastic particles in geological layers, sudden changes in carbon isotope ratios indicating massive combustion of fossil fuels, and perhaps increases in certain metal concentrations from industrial processes. Have we found any such anomalies? The Paleocene-Eocene thermal maximum 56 million years ago shows a rapid carbon isotope excursion and global warming. Could this have been an industrial civilization burning through their fossil fuels? Almost certainly not. The timescale is wrong, and there are clear geological mechanisms to explain it. But the question highlights how little evidence an ancient civilization might leave. More speculatively, if such a civilization reached sufficient technological advancement, they might still be here, hidden deliberately, observing us from bases in inaccessible locations, or having transitioned to post-biological forms that leave no fossil record. This explanation strains credibility in its strong forms. It requires extraordinary secrecy and raises the question of why they wouldn't make contact. But in weaker forms, that intelligence has evolved multiple times on Earth in species we don't recognize as comparable to ourselves. It's worth considering. Cetaceans, corvids, cephalopods, elephants all demonstrate sophisticated cognition. They're not technological, but they're intelligent. Perhaps we're too focused on our particular evolutionary pathway and miss other forms of mind. Chapter 8. What the silence means for us. The Great Silence is not merely an abstract puzzle for cosmologists to ponder. It carries profound implications for how we understand ourselves, our place in the universe, and our future. The weight of cosmic responsibility. If we are alone, truly alone, not just in our galaxy, but across vast reaches of space and time, then we bear a responsibility of almost unbearable magnitude. We are not merely a species trying to survive and flourish. We are the universe's only means of knowing itself. Consider what consciousness represents. For 13.8 billion years, the universe evolved according to physical law. Stars formed and died, galaxies collided, planets coalesced, but none of it was witnessed. There was no subjective experience, no what it is like to be anything. The cosmos was vast and complex, but essentially unconscious. Then, in at least one location, matter organized itself into configurations capable of self-awareness. Atoms forged in stellar cores, scattered by supernova, accumulated on a planet's surface and began to think. Through us, and possibly only through us, the universe opened its eyes. Every human being who has ever lived contributed to this miracle. Every thought, every act of creativity, every moment of love or wonder represents the cosmos experiencing itself. When we look at the stars, We are the universe looking back at its own history. When we unravel the laws of physics, we are the universe deciphering its own operating system. If we're the only instance of this awakening, then our continuation is not just important to us, it's important cosmically. Our extinction wouldn't merely end one species' story. It would close the universe's eyes, return the cosmos to unconsciousness, make all that vast complexity meaningless once more. This is not a religious claim, but a materialist one. If consciousness is a natural phenomenon that emerges from certain physical configurations, and if those configurations are extraordinarily rare, then consciousness itself is rare. And anything rare has value proportional to its scarcity. We don't know if we're alone, but the great silence suggests we might be, or at least that consciousness is far rarer than we hoped, and that possibility should fundamentally change how we view our obligations to future generations. The implications of filters ahead. If the great filter lies ahead of us, if most civilizations destroy themselves shortly after achieving technological capability, then we face an urgent imperative. We must be different. We must be among the few who navigate the danger successfully. This requires honest assessment of the risks we face. It requires moving existential risk from the periphery of political concern to its centre. It requires long-term thinking and global cooperation on a scale we've rarely achieved. Nuclear weapons remain with us, arsenals still capable of civilizational destruction despite post-Cold War reductions. The knowledge of how to build them cannot be unlearned. As long as nations remain armed with these weapons, the possibility of their use, through accident, miscalculation, or deliberate choice, persists. Climate change accelerates despite decades of warnings. We continue to pump greenhouse gases into the atmosphere at rates that could trigger irreversible feedback loops. The question is not whether we can solve this problem technically, we have the technology for clean energy, but whether we will implement solutions fast enough and at sufficient scale. Biotechnology advances rapidly, often ahead of safety frameworks and governance structures. We're gaining the ability to modify life at its most fundamental level, but we're doing so in a world where thousands of laboratories operate with varying levels of security and oversight. The risk of accidental or deliberate release of dangerous pathogens increases each year. Artificial intelligence development proceeds at breakneck pace, driven by economic competition and military applications. We're creating increasingly capable systems without fully understanding how to ensure they remain beneficial and under human control. The challenge is that by the time we know we've created something too intelligent to control, it may already be too late to establish that control. These are not distant theoretical dangers. They are present, growing risks that could materialize within our lifetimes or our children's lifetimes. If the great filter awaits civilizations at roughly our stage of development, these are likely the mechanisms through which it operates. The encouraging aspect is that these are all problems of our own making, which means they're potentially problems we can solve. We built nuclear weapons. We can choose not to use them and eventually dismantle them. We altered the climate. We can stabilize it through emission reductions and carbon removal. We developed dangerous biotechnology. We can implement robust safety protocols and international monitoring. We're creating AI. We can invest heavily in alignment research and cautious safety-focused development. But time is not unlimited. Technologies that could go catastrophically wrong are advancing faster than our wisdom in managing them. We're in a race between our growing power and our growing wisdom, and it's genuinely uncertain which will win. The value of diversity and redundancy. If we are rare, if consciousness is precious, then its preservation becomes paramount. This suggests specific strategies. First, redundancy. A civilization confined to a single planet faces single points of failure. A large asteroid impact, supervolcano eruption, nearby supernova, or any number of cosmic threats could end everything. Establishing self-sufficient colonies on other worlds, Mars orbital habitats, eventually other star systems, creates backup copies of human civilization that could survive even if Earth were destroyed. This is not about abandoning Earth or viewing it as disposable. Earth is our home, the only world we know that's naturally habitable, but it's also fragile, and putting all of humanity's eggs in one planetary basket is a tremendous risk. Second, diversity. Monocultures are vulnerable in agriculture, in ecosystems, and in civilizations. A single global culture, a single political system, a single economic model creates systemic risks. If it fails, everything fails together. Maintaining cultural, political, and technological diversity increases the chance that some approaches will survive, even if others fail catastrophically. This suggests being cautious about total global integration. Whilst cooperation is essential for solving planetary challenges, some degree of decentralization and autonomy might provide resilience. If one region's experiment with AI development goes disastrously wrong, others might be insulated and learn from the failure. Third, long-term thinking. Most human institutions operate on timescales of years or decades. Corporations focus on quarterly earnings. Politicians think in election cycles. But the challenges we face require thinking across centuries and millennia. We need institutions designed for long-term stewardship. Organizations whose mandate is to consider how decisions made today will affect humanity 1,000 years hence. We need legal and economic structures that internalize long-term costs and benefits, not just immediate ones. Some civilizations have achieved this. The Iroquois Confederacy's Great Law of Peace supposedly required decisions to be evaluated for their impact 7 generations into the future. While the historical accuracy of this specific claim is debated, the principle itself, that we should consider the long-term consequences of our choices, remains profoundly important. The search must continue. Despite the silence, despite the absence of signals, we must continue searching. SETI, the search for extraterrestrial intelligence, represents more than just a scientific program. It's an expression of hope, of refusal to accept isolation without exhausting every possibility. The search has evolved beyond simply listening for radio signals. We now look for technosignatures, any indication of technological activity. This includes optical SETI, searching for laser pulses that could be deliberate beacons or leaked communications. It includes searching for infrared excess around distant stars that might indicate megastructures harvesting stellar energy. It includes looking for unusual atmospheric compositions on exoplanets that might suggest industrial activity. We search because the cost of searching is low and the potential payoff is infinite. If we detect intelligence, even just once, even just a signal confirming we're not alone, it would transform human civilization. It would answer the deepest question we've ever asked. It would show us that the great filter, if it exists, can be passed. It would give us hope and perhaps guidance for our own future. And if we never find anything, if the silence persists despite centuries of increasingly sophisticated searches, that too tells us something. It tells us that we may bear cosmic responsibility alone. That our continuation matters not just to us, but to existence itself. Chapter 9. Paths Forward. Choosing our cosmic destiny. We stand at a threshold. Our species has existed in its current form for approximately 300,000 years. For the vast majority of that time, we lived in small groups, hunter-gatherers, whose technology barely changed across millennia. Then, in the blink of a cosmic eye, the last 10,000 years, we developed agriculture, cities, writing, science and technology that allows us to split atoms and edit genes. We've reached a point where we can destroy ourselves completely or expand beyond Earth and potentially survive for millions or billions of years. The decisions we make in the coming decades and centuries will likely determine which path we take. Embracing wisdom alongside power. Our species' defining characteristic has been our ability to manipulate our environment through technology. We are tool makers, problem solvers, innovators. This has brought us extraordinary power, but power without wisdom is dangerous. Wisdom, in this context, means several things. It means understanding the long-term consequences of our actions, not just the immediate benefits. It means recognizing that not every problem has a technological solution, and some solutions create worse problems than they solve. It means humility about the limits of our knowledge and the unpredictability of complex systems. It also means developing what philosopher Nick Bostrom calls cosmic endowment, a sense of responsibility not just to present generations, but to all future generations, and not just to humanity, but to the potential for consciousness and flourishing throughout the cosmos. This requires changes to how we think and act. It requires educational systems that emphasize long-term thinking, ethical reasoning, and systemic understanding alongside technical skill. It requires political and economic systems that reward foresight rather than short-term gain. It requires cultural narratives that celebrate stewardship and wisdom as much as innovation and power. We have examples of this kind of thinking in various philosophical and spiritual traditions. Indigenous wisdom traditions often emphasize living in balance with nature, taking only what's needed and considering the welfare of future generations. Certain religious teachings stress humility, compassion, and recognition of our place within a larger whole. Secular philosophical movements like long-termism and effective altruism explicitly focus on maximizing well-being across vast temporal scales. The challenge is to integrate these insights into global civilization at a time when technology-driven change accelerates and immediate pressures dominate attention. But if we fail to do so, we may become just another civilization that briefly flickered and fell silent. Global cooperation on existential risks. No single nation can address existential risks alone. Climate change doesn't respect borders. A pandemic released anywhere can spread everywhere. Artificial intelligence developed without adequate safety measures in any country poses risks to all countries. Nuclear weapons anywhere threaten everyone everywhere. This necessitates unprecedented levels of international cooperation. We need robust global institutions capable of coordinating responses to planetary threats. We need treaties and agreements that all major powers genuinely commit to. We need transparency and verification mechanisms so nations can trust that others are complying with safety agreements. This is politically difficult. Nations guard their sovereignty jealously. Cooperation requires trust, and trust is often in short supply between powers with different values, political systems, and historical grievances. But difficulty doesn't equal impossibility. We've achieved significant international cooperation before. The Antarctic Treaty, the Outer Space Treaty, the Montreal Protocol on ozone-depleting substances, nuclear non-proliferation agreements, when threats were clear and mutual benefit was recognized. The key is making existential risks vivid and immediate enough that they overcome short-term incentives to defect from cooperation. This is a challenge of communication and political will as much as technical policy. We also need to develop new norms around emerging technologies. Just as we've developed norms against chemical and biological weapons, we need norms around AI safety, biotechnology research standards, and geoengineering. These norms should be established before catastrophes occur, not after. Becoming a multiplanetary species. While solving problems on Earth must be our priority, we should also pursue expansion beyond Earth. This serves multiple purposes. Practically, it provides redundancy. A civilization on multiple worlds is vastly more resilient than one confined to a single planet. Even if Earth suffered a catastrophe, human civilization and consciousness could continue elsewhere. Psychologically, it provides hope and purpose. The space program has historically inspired people, demonstrating what humanity can achieve when we work together toward ambitious goals. A renewed commitment to space exploration could serve similar functions, uniting people around a positive vision of the future. Scientifically, it advances knowledge. Establishing colonies on Mars or orbital habitats requires solving problems in closed-loop life support, radiation shielding, resource utilization, and long-duration space travel. These solutions have applications on Earth as well: sustainable systems, recycling technologies, energy efficiency, and philosophically, it represents a commitment to the long-term future. It's a declaration that we intend to be around for the long haul, that we're thinking beyond the next election cycle or fiscal quarter to timescales of centuries and millennia. Space expansion doesn't mean abandoning Earth. Our home planet should remain the centre of human civilization and the focus of our care. But diversifying beyond Earth makes our species and consciousness itself more secure. Cultivating cosmic perspective. Perhaps most importantly, we need to develop what Carl Sagan called the cosmic perspective, an understanding of our place in the vast universe, a recognition of our shared humanity in the face of cosmic scale, and a sense of responsibility to the future. When astronauts see Earth from space, many report a profound shift in consciousness, the overview effect. From orbital distance, national borders disappear, political conflicts seem petty. The atmosphere appears as a thin, fragile veil, protecting everything we've ever known. The dominant feeling is one of unity and vulnerability. We need to cultivate this perspective, even for those who never leave Earth's surface. We need education that teaches not just facts about the universe, but wonder at its scale and beauty. We need cultural narratives that emphasize our common humanity and common fate. We need to internalize the truth that we share one planet, one origin, one history, and potentially one future. This cosmic perspective doesn't diminish human concerns, it contextualizes them. Personal struggles remain important, but they're held within awareness of our larger situation. Political differences remain real, but they're tempered by recognition that we're all temporary passengers on this planet, and our descendants will judge us by whether we left them a livable world and a flourishing civilization. The great silence, whatever its cause, reminds us that conscious life might be rare and precious. Every child born, every act of creativity, every moment of connection between people represents something potentially unique in the cosmos. This should make us more committed to preserving and enhancing life, not less. The choice before us. We cannot know with certainty whether the great filter lies in our past or future. We cannot know if we're alone or merely first, or if others exist but remain hidden or undetectable. We cannot know if we'll survive the coming centuries or become another silent voice in the cosmic void. But we can know that our choices matter. We can know that the effort to survive and flourish is worth making. We can know that consciousness, the universe's ability to know itself, is precious beyond measure. If we are alone, then we carry the universe's only light. If we're not alone, then we represent one small flame among many, and our responsibility is to keep that flame burning so that eventually we might find others and no longer face the darkness alone. Either way, the path forward is the same: wisdom, cooperation, caution with our growing power, and determination to become a civilization worthy of the cosmos that created us. The great silence will persist, perhaps forever, but within that silence we can create meaning. We can build a civilization that lasts not just centuries, but millions of years. We can expand beyond our cradle world and eventually reach for other stars. We can transform ourselves while remaining human in the ways that matter most, curious, compassionate, creative. We can choose to be the ones who pass through the filter, who navigate the dangers, who become the answer to Fermi's question rather than another example of its puzzle. The universe is watching through our eyes, waiting to see what will become. The silence surrounds us, vast and patient, and in the face of that silence, we must decide, will we add our voice to the cosmic void, or will we persist, evolve, and eventually break the great silence, not by detecting others, but by becoming the civilization we've been searching for? Wise, ancient, and unafraid. The choice, as always, is ours. Thank you for joining Sleep Entangled on this journey through one of existence's deepest mysteries. The question of why we don't see aliens touches something fundamental in us: our loneliness, our hope, our fear, and our wonder. As you drift towards sleep tonight, carry with you this truth: you are matter that has become aware of itself, a small part of the cosmos that can contemplate the whole. Whether we're alone or merely waiting to find others, your consciousness is precious beyond measure. If these cosmic questions stir something within you, subscribe to Sleep Entangled and let curiosity guide your nights. Like this video if it brought you peace or provoked new thoughts, and share it with others who find wonder in the great unknown. May your dreams be filled with starlight and possibility. Until we meet again beneath the cosmic canopy, rest well.